So the James Webb Space Telescope is about 1 million miles away from Earth. It's at a place in space we call the L2 point, Lagrange 2.
Positioned approximately 1 million miles from Earth, the James Webb Space Telescope orbits at a unique gravitational equilibrium known as Lagrange Point Two. Its mission is extraordinary: to peer deeper into the cosmos than any telescope before it, capturing the faint light of the earliest stars, galaxies, and phenomena that shaped the universe. Initially set to conduct routine observations, Webb quickly uncovered astonishing signals and patterns that defy prior assumptions about the nature of space and time. Neptune's cooling mystery and magnetic pulse. Neptune, the solar system's eighth and most distant planet, has long been considered a stable ice giant. A cold, distant world with a thick atmosphere composed primarily of hydrogen, helium, and methane. For decades, scientists believed its climate and magnetic environment were relatively constant. However, James Webb's recent observations tell a different story, one that challenges decades of understanding and raises profound questions about planetary physics. Between the years 1970 and 2020, scientists observed a steady cooling of Neptune's upper atmosphere by nearly 10 degrees Celsius. This temperature drop is significant. To put it in perspective, such a cooling is far beyond what would be expected from minor fluctuations in solar radiation or internal planetary processes. Neither changes in the Sun's activity nor Neptune's internal heat generation, typically caused by gravitational contraction and radioactive decay, explain this phenomenon. Neptune's atmosphere is responding to some unknown factor, one that remains invisible yet powerful. Further deepening this mystery, Webb's instruments detected a faint but steady rhythmic pulse in Neptune's magnetic field. Unlike chaotic or random signals caused by solar wind or the planet's moons, this magnetic pulse repeats with clockwork precision, resembling a heartbeat emanating from the planet's interior. This steady oscillation could not be accounted for by any known physical process, including interactions with the solar magnetic field or gravitational disturbances. Some experts hypothesize that the cause could be fluctuations in dark matter. This mysterious form of matter does not emit or absorb light, but exerts gravitational influence across the universe. If regions of denser dark matter pass near Neptune, they might subtly influence its magnetic environment, causing the observed pulse and atmospheric cooling. Others consider more speculative theories, suggesting an unknown external force or even artificial manipulation. While no evidence currently supports extraterrestrial interference, the sheer enigma of these signals invites an open mind and deeper investigation. What unseen forces shape Neptune's mysterious heartbeat and sudden chill? Could this distant planet be signaling something extraordinary, unveiling two water-rich, possibly habitable worlds? The TRAPPIST-1 system, a red dwarf star located approximately 39 light-years from Earth, has been a cornerstone in exoplanet research since its discovery in 2016. Hosting 7 rocky planets, this system offers a unique laboratory for studying planetary formation and habitability. Most compellingly, 3 of these planets orbit within the star's habitable zone, the region where temperatures might allow liquid water to persist. Until now, much of our understanding of TRAPPIST-1's planets relied on indirect measurements and theoretical models. James Webb's cutting-edge infrared spectrometry has revolutionized this knowledge by directly probing the atmospheric composition of these worlds, particularly TRAPPIST-1d and TRAPPIST-1e. Webb detected dense water vapor in the atmospheres of both planets, signaling the presence of thick, humid envelopes. This goes far beyond trace amounts of moisture. The data suggest climates that could resemble Earth's tropical or subtropical zones, with abundant water cycling through the atmosphere and surface. Even more intriguing is the detection of ozone-like compounds in the same atmospheres. On Earth, ozone is a byproduct of biological processes, generated when oxygen molecules interact with ultraviolet sunlight. While the presence of ozone elsewhere does not guarantee life, it is a promising biosignature, indicating atmospheric chemistry potentially influenced by living organisms. These findings elevate TRAPPIST-1d and TRAPPIST-1e from theoretical possibilities to real candidates for hosting life. They push scientists to consider not only if life could exist there, but whether it might already thrive under conditions similar, though not identical, to our own planet. This discovery also fuels the ongoing debate about how common habitable planets are in the galaxy. If multiple planets within a single system show such promise, the Milky Way could harbour countless other life-friendly worlds, reshaping humanity's search for extraterrestrial life. If two planets in the same system have water and ozone, how many more life-sustaining worlds await discovery? Ancient galaxy JD SGS130. One of James Webb's most profound achievements lies in its ability to peer back in time, observing galaxies formed shortly after the universe's birth. Among the earliest is the galaxy known as JD SGS130, which existed a mere 330 million years after the Big Bang, a cosmic infant barely beginning to grow. Webb's observations revealed this galaxy emitting unusually strong Lyman alpha radiation, ultraviolet light emitted by hydrogen gas during star formation. Normally, such radiation would be absorbed by neutral hydrogen, filling the early universe, preventing it from traveling unimpeded. However, the hydrogen gas surrounding JD SGS130 appears to be ionized, meaning its atoms have been stripped of electrons, allowing Lyman alpha radiation to pass freely. This discovery challenges the accepted timeline of cosmic rionization, the era when the first stars and galaxies transformed the universe's foggy hydrogen gas into transparent space. Previous models suggested this process occurred much later, but JD SGS130 indicates that ionization happened sooner and perhaps more rapidly than scientists believed. What mechanisms caused this early ionization? It might be intense radiation from the galaxy's earliest stars, powerful black hole activity, or unknown energy sources. This galaxy's light is a direct message from the universe's earliest chapters, urging astronomers to rethink the cosmic dawn. Understanding this process is crucial because it marks the universe's transition from darkness to light, laying the groundwork for the formation of stars, planets, and, ultimately, life. Could JD SGS130 reveal hidden forces that accelerated the universe's awakening? What does this mean for cosmic evolution? White dwarfs and surviving planets. White dwarfs are dense, cooling remnants of stars like our Sun after they exhaust their nuclear fuel. Traditionally, any planet orbiting close to such stars was expected to be destroyed by intense radiation and heat. However, James Webb's observations in the system WD 1856534 reveal a large gas planet orbiting unusually close to its white dwarf host. Despite the harsh environment, this planet remains stable. Webb's instruments detected water vapor, sulfur compounds, and other chemicals in its upper atmosphere, suggesting that it sustains and possibly regenerates its atmosphere. This finding defies expectations and challenges established views on planetary survival near dead stars. The implications are profound. If planets can endure the death throes of their stars and maintain habitable conditions, this expands the possible locations for life in the universe. It raises exciting questions about the existence of ecosystems that might adapt to survive extreme energy conditions around white dwarfs. Such resilience could imply that life may not only survive, but thrive in environments previously considered inhospitable, providing new hope for discovering life beyond Earth. Could life flourish around dead stars? What secrets do these planetary survivors hold for astrobiology? The mysterious moons of Uranus and Neptune. For decades, the small moons orbiting Uranus and Neptune were dismissed as cold, inert frozen rocks drifting silently through space. These distant moons, such as Hippo and Despina, were thought to be geologically dead due to their great distance from the Sun and lack of internal heat sources. However, James Webb's infrared observations have turned that assumption on its head. Webb's sensitive instruments detected unexpected thermal emissions from several of these moons, indicating the presence of internal heat. Despite the extreme cold of the outer solar system, these moons appear to be geologically or cryovolcanically active. Cryovolcanism refers to the eruption of volatile substances like water, ammonia, or methane rather than molten rock, suggesting subsurface oceans or pockets of heat beneath the icy crust. What powers this hidden internal heat? Scientists have proposed several mechanisms. Radioactive decay of elements inside the moon's rocky cores can generate heat over billions of years. Tidal heating, the stretching and squeezing caused by gravitational interaction with their parent planets, can also generate internal friction and warmth. Yet, these processes do not fully explain the organized presence of complex carbon compounds detected on the surfaces of these moons. James Webb identified organic molecules on these moons, compounds that serve as precursors to life on Earth. The presence of such organics in cold, distant environments challenges existing ideas about where life's building blocks can form. If these moons possess subsurface oceans rich in organics, they may represent potential habitats for microbial life or prebiotic chemistry. The discovery invites comparisons to other icy worlds, such as Jupiter's moon Europa and Saturn's moon Enceladus, which have already become prime targets in the search for extraterrestrial life. Uranus and Neptune's moons, previously overlooked, may now emerge as important players in understanding the limits of habitability in our solar system. Could these frozen moons conceal oceans teeming with life's ingredients? What other surprises await beneath their icy shells? A rhythmic pulse. From the Cigar Galaxy. Messier 82, known as the Cigar Galaxy due to its elongated shape, has long fascinated astronomers for its intense star formation and energetic supernova activity. Situated about 12 million light-years from Earth, this galaxy is a nearby cosmic laboratory for studying stellar birth and death. Yet James Webb has uncovered something truly baffling within its core. Webb detected a repeating infrared pulse emanating from the heart of Messier 82. Unlike random cosmic noise, this pulse exhibits a highly regular rhythm with a fixed interval and duration, suggesting deliberate modulation rather than natural chaos. Such a precise pattern is reminiscent of signals sought in the search for extraterrestrial intelligence, known as SETI, where scientists look for structured transmissions from advanced civilizations. The source of this pulse remains unidentified. One natural explanation could be a rapidly spinning neutron star or pulsar emitting in the infrared spectrum, but Webb's data found no matching signals in visible light or X-rays typically associated with these objects. This raises profound questions. Is this pulse a product of exotic astrophysical phenomena unknown to current science? Or could it be the faint residue of an ancient technological signal from a civilization long gone? While it is premature to draw conclusions, the discovery adds a tantalizing possibility to the mystery of the universe. As astronomers continue to analyze the signal, it challenges us to remain open to the unexpected and consider that the cosmos might harbor intelligence in forms we are just beginning to imagine. Could the rhythmic pulse from Messier 82 be a cosmic message? What secrets might this enigmatic signal hold? The mystery of Tabby's star. Tabby's star, officially known as KIC 846285-2, has puzzled astronomers since its discovery due to its irregular and dramatic dips in brightness. These fluctuations defied typical explanations, such as passing comets or dust clouds. When James Webb focused its precise instruments on Tabby's star, it did not resolve the mystery, but deepened it. Webb's photometric sensors revealed that the objects causing the dimming events are flat, angular, and possibly massive. These shapes are unlike any natural astronomical bodies, which tend to be spherical or irregular. Such geometric forms suggest the possibility of artificial origin, sparking speculation about megastructures built by advanced civilizations, sometimes referred to as Dyson swarms, hypothetical constructs designed to harness the energy of a star. Furthermore, Webb detected an unusual infrared glow surrounding Tabby's star. This glow could be thermal radiation emitted by artificial structures absorbing and re-radiating stellar energy. The presence of this infrared excess aligns with the theory of engineered constructs rather than natural dust clouds. While these findings do not confirm extraterrestrial technology, they keep the door open to possibilities far beyond current understanding. Tabby's star stands as a compelling enigma at the crossroads of astrophysics and the search for intelligent life. Could Tabby's star host alien megastructures? What extraordinary phenomena hide behind its mysterious dimming? The cosmic implications. The discoveries made by the James Webb Space Telescope challenged the long-held notion of the universe as a cold, indifferent place. Instead, they paint a picture of a dynamic, interconnected cosmos filled with mysteries and possible signs of life, intelligence, and resilience. Neptune's magnetic pulses, water-rich exoplanets, early cosmic ionization, planets surviving stellar death, active icy moons, enigmatic galactic signals, and possibly artificial structures all compel us to expand our understanding of the cosmos. Each revelation forces scientists to rethink how galaxies evolve, how planets form and endure, and how life might emerge in environments once considered hostile. These findings do not provide all the answers, but ignite new questions that will fuel research and exploration for decades to come. Moreover, the James Webb Telescope invites us to ask profound philosophical questions. Are we alone? Is the universe watching us as much as we are observing it? The subtle signals and unexpected phenomena remind us that space is a vast frontier of discovery, with secrets waiting to be uncovered. As technology advances and observations continue, humanity stands at the dawn of a new era in cosmic understanding, one in which the universe may seem less foreign and more familiar. What new mysteries will the James Webb Telescope uncover next? Are we truly ready to face the cosmos's hidden truths? The role of infrared astronomy in unlocking cosmic secrets. One of the most revolutionary aspects of the James Webb Space Telescope is its ability to observe the universe in infrared light. Unlike visible light, infrared waves can penetrate cosmic dust clouds that typically obscure objects in space. This capability allows Webb to see stars and galaxies forming behind veils of gas and dust, effectively unveiling regions that were previously hidden from view. Infrared astronomy is crucial for studying the earliest epochs of the universe, moments after the Big Bang, when the cosmos was filled with dense clouds of hydrogen gas. As the universe expanded and cooled, the first stars ignited within these clouds. However, the ultraviolet and visible light emitted by these stars is largely absorbed by surrounding material, making them invisible to conventional telescopes. Infrared light, with its longer wavelengths, passes through these clouds, revealing the birthplaces of stars and galaxies. Webb's advanced instruments, including the near-infrared camera and mid-infrared instrument, enable astronomers to analyze the chemical composition, temperature, and motion of celestial bodies. This allows scientists to better understand star formation rates, galaxy evolution, and the interstellar medium's properties. Infrared observations also play a critical role in exoplanet research. By detecting the heat signatures of planets orbiting distant stars, Webb can study their atmospheres, temperature profiles, and potential biomarkers, signs of life-related chemistry. The use of infrared light is transforming our understanding of the universe from its earliest moments to the present day. Webb's infrared vision is a powerful tool that pierces the darkness, uncovering mysteries that were once thought forever beyond reach. How many more hidden wonders lie cloaked in cosmic dust, waiting for infrared light to reveal them? Will Webb's infrared eyes reshape astronomy forever? The implications of early galaxy formation on cosmology. The discovery of galaxies, such as JD SGS130, forming only 330 million years after the Big Bang, forces cosmologists to re-evaluate their models of early galaxy formation and evolution. Traditional theories suggested that galaxies gradually assembled over hundreds of millions of years through mergers and star formation in smaller structures. Webb's observations suggest that some massive galaxies formed surprisingly early and emitted intense radiation that influenced their surroundings. This accelerated timeline means that the early universe may have undergone rapid transformations, creating large, mature galaxies far sooner than predicted. Such findings impact our understanding of dark matter's role, gas dynamics, and star formation efficiency in primordial galaxies. Furthermore, the strong Lyman alpha radiation escaping JD SGS130 suggests that regions of the early universe became ionized patchily and unevenly. Instead of a uniform reionization, the process may have been driven by these early luminous galaxies, creating bubbles of ionized gas that eventually merged. This nuanced view complicates but enriches the cosmological picture. It suggests that the universe's early history was dynamic and heterogeneous, with pockets of rapid activity shaping the cosmic landscape. Understanding this process has broader implications. It informs how matter clustered to form the large-scale structure of the cosmos, influences cosmic microwave background radiation interpretation, and guides the search for the universe's earliest light sources. Could early galaxies like JD SGS130 rewrite cosmic history? How will this reshape our understanding of the universe's origin, white dwarf systems, and the potential for post-stellar habitability? White dwarfs are fascinating remnants of stars that have exhausted their fuel and shed their outer layers. They are incredibly dense and hot initially, cooling slowly over billions of years. For decades, the consensus was that planets orbiting white dwarfs could not support life because of the intense radiation and heat sterilizing nearby environments. James Webb's surprising detection of a large gas planet orbiting WD 1856534, with a stable atmosphere containing water vapor and sulfur compounds, upends this assumption. The persistence of such an atmosphere implies mechanisms for atmospheric regeneration or protection from the white dwarf's harsh environment. Scientists theorize that planets could migrate inward after the host star's death, or capture new atmospheres over time. Some suggest tidal locking, where one side permanently faces the white dwarf, might create habitable zones with temperate conditions. These scenarios open exciting possibilities for life to arise or endure even after stellar death. If life could adapt to such extremes, it expands the potential habitability criteria beyond traditional Goldilocks zones and forces us to broaden our perspective on where life might exist in the universe. Such findings emphasize the need to study white dwarf systems carefully. They may harbor exotic biospheres fueled by energy sources unlike our Sun, perhaps relying on stellar remnants or geothermal heat. Thanks for joining us on this cosmic journey. Don't forget to comment your thoughts below and watch our next video for more mind-blowing space discoveries.